Hello class. Today we are going to discuss different login protocols. So this is the concept of how we apply cryptography to the challenge of creating secure logins, both for local computers and for more complex web-based systems. So with that, let's go kick it off with an overview, beginning with some motivating examples. So the first principle at play here is that different systems require different kinds of security. The way you could think about this is that if you had $100 in a tin box, you wouldn't put a $5,000 titanium lock on it, right? You would put a simple $5 lock from the dollar store on it. But if you had a bank vault, you would put a much more complicated lock on that kind of vault. So these different systems demand different kinds of security. One example of this is if you're trying to unlock your phone or a local computer. This is like sticking a key in a door. When you're unlocking a door, a key is really what you need. And so unlocking your phone and your computer, you kind of just need a key to unlock things. However, if you are using a key fob in a car, then we need to design such that no one can replicate what your key fob does by just listening to the radio waves, right? We need that to be slightly more secure. And lastly, if you're trying to pay for groceries and someone steals your credit card information, in a perfect protocol, we wouldn't allow someone to reuse that interaction and reuse your credit card. So as you can see, right, no one can record the interaction of you sticking your key in a door. So that doesn't really need to have the same kind of security that you need when someone can record and adversarially interact with your protocol. So with that, another example is if you're the victim of a phishing attack, it'd be great if someone couldn't reuse the credentials that they stole through the phishing attack to log into your systems. So as we kind of laid out in those examples, there are a few different attack modes, right? One mode is direct attacks. These use only publicly available parameters to directly attack the login system. Then there are eavesdropper attacks. These attacks involve listening in on the transcriptions of the interactions. Next, we have active attacks. This is where the malicious eavesdropper is also providing malicious interactions. So if we go back here, this is an example of a direct attack. This is an example of a eavesdropper attack. And these two are examples of active attacks, or in some cases maybe very advanced eavesdropping attacks. So those are the three different attack types. This means we need a couple different key types. The first key is a secret key. This is where the verifier keeps their verification key private. The second type is a public key, where the verifier keeps their verification key public. Between these two, which would you prefer? So would you prefer using a secret key, or would you prefer using a public key? The benefit to keeping the secret key is that all the information is totally private. The benefit to the public key is that the system's fully auditable. We actually tend to prefer public keys because if we use public keys, then the key being leaked does not cause any problems. Next, a principle at play here is state. So there are stateful protocols where verification and secret keys are updated at every login, and there are stateless protocols where verification and secret keys do not change. Which of these do we prefer? Well, after some brief examination, we notice that stateful protocols introduce a new potential place for error or for manipulation, where the state might be incorrect. With a stateless protocol, we have the benefit of the state not really mattering. So this results in a slightly more stable security protocol. So there are a lot of benefits using these kinds of stateless protocols. So with that, let's talk about some direct attacks. So, direct attack security. The most basic password is, the basic thing is that, you have your, oopsie daisies, these are looking kind of funky. Sorry about that. So the most basic concept is that the verification key of the server is just the same thing as the password, right? So we have our server here, and we have our, right? So this guy is prover, this guy is verifier. Let's label them. Prover, verifier. Prover sends the secrets key to the verifier, who then outputs whether the verification key is equal to the secret key. So you can see this is the most basic security. Well, are there any problems with this notion of security? Well, if the server's compromised, the password's leaked, right? If you go back here, the verifier has to store the verification key on the server itself, right? There's some kind of database like this. And you have the verification key. And the problem with this is that if someone gets a hold of the server, the password is leaked, and then it's compromised. So the most basic solution to this is you store a hash value of the password on the server and compare it to stored values, right? So we have the same thing. We have the prover, who has the secrets key. They send the secret key to the verifier, who then has the verification key, which we already know is just the hash of the secret key. So this is better, right? Now, if the server is hacked and its information is leaked, well, the verification key is just the hash of the secret key. And since hashes are one-way functions, there isn't a huge security threat. Some of the able to reverse a hash function because that's, they can solve that problem. They have more space in the universe. So the flaw is that if you listen once, that reveals the secret key, right? Any eavesdropper here, here's the secret key. So that's kind of it's better, but it doesn't solve for eavesdroppers. So that's one flaw. Next, we're going to discuss online dictionary attacks. If you think someone's password is from a common password list, you can just try the most common password, right? So that's like 1, 2, 3, 4. Actually the word password itself is quite common. Right, so you just pick these common passwords and try them. So the way that attack works is you have the, we'll say MP for malicious prover, and we have our honest verifier. And they just send all of the different secret keys that are from this list of common passwords. And the honest verifier just tests them. And eventually, if they're in the secret key list, which happens about 10% of the time, then the honest verifier will be tricked into letting the malicious prover get through it. So how do you solve this problem? every 2 failed attempts, you double the response time. So secret key 1 fails, secret key 2 fails, then you need to wait, there's a little clock there, a certain amount of time before you can try going again, right? So you try again and you try again, and then your time is doubled. So as you can see, the system stops you from just spamming the bot online. Now that doesn't protect against what's known as an offline dictionary attack. So if the server is compromised, the attacker could just steal the password database. And you can run a hash function locally and compare it to the database and then you crack the passwords. So in the database, right, you have your verification key that corresponds to this complicated hash. And you can just brute force passwords from your list until you hit that verification key. Not only that, if you use GPUs, you can do thousands of these operations per second. So you can get through this thing super quickly. And you don't even always need to crack the server security for this kind of attack. You can buy the old server hard drives from the company and recover data from this. This actually happens to eBay right here. This eBay fell victim to this kind of vulnerability. And about half the passwords, according to a study, are contained in this password list that was produced by researchers, according to estimations. So using random passwords is extremely important, and it protects from dictionary appointments. So random passwords, these foil dictionary attacks. Okay, so we have to recognize that users are not perfect, and they're going to sometimes use non-random passwords. So with that, we need to do something called salting a password. And what salting a password does is it protects the password by adding a little bit of randomness to it. This should hopefully feel like a familiar cryptographic concept, right? The idea of adding randomness to something to give it security is very common in cryptography. So salts are just random bits of information that are hashed along with the verification key and stored in the clear. So in your database, now you actually have the verification key plus you have the hashed verification key, and the verification key is hashed with the salt. The salt is represented by N, and this is publicly known. This means that in order for someone to actually hack the passwords, they have to hash every single password each time. You can imagine if you didn't salt, you could just hash all the passwords at once and then reuse that hashed list for just direct compares. This would reduce your runtime because you don't need to actually run the hash function for every single salt. But with this approach, it forces the adversary to actually run the attack each time. So there's some benefit there. And that's known as a pre-processing attack. So a pre-processing attack is when you pre-generate all the hashes before you run a comparison against the database. So this helps against that. But if you use weak passwords, you can still do a flavor of an online dictionary attack locally and crack this fairly quickly. So that's public salts. Well, this is cryptography, right? We take public and instead we say secret. So secret salting is when you assign a very small random variable. This random variable, we'll call it t. You know, it's like zeros and ones, and there's like maybe 7 of them. And this means that you need to try to that means that for every password, there are 2 to the 7th possibilities of other passwords. So you have the password plus one of these, and you run that through your hash function to unlock something. Now the beauty of secret salts is that the server doesn't even know the secret salt. But the server can brute force this for an individual password in like 100, very quickly, within half a second. So fast enough for the user to log in. And so what this does is this allows us to mean that yes, you do more work on every login, but it increases if you're trying to hack a password, you have to do 2 to the 7th iterations per password. That's going to massively increase your runtime for cracking. So secret salting is actually quite clever. The next sort of clever concept is slow hash functions. So, any individual user logging into a system, they won't notice a slow hash function that is, way slower than SHA-256. But an attacker will know, right? So if you have, let's say SHA-256 takes this long. This is SHA. Then you have the slow one, call it R, and the slow function takes like that long. For a single password, both of those are way less than a second, right? But if you're an attacker, doing this one doing that one 1 trillion times is way faster than doing this one 1 trillion times. So, an important principle when making these hash functions slow is we need to make sure that their memory access is also kind of random. So you have a hash function, and this is your memory, and all your data for your hash function is stored in your memory in neat little rows. This makes it possible to design specialized hardware for the hash function and make it faster. What you really want is your memory to look like this. A bunch of blocks, line, useless information, squiggles, exclamation point, Q, line, semicolon. So here, it's way harder to access memory in this section than it is in this section. And that itself will prevent you from creating specialized hardware and allowing you to make that slow hash function faster. So if you're making a slow hash function, not only does it actually need to be hard to do the computation, but also it needs to have characteristics that make it hard to implement in hardware. And the easiest characteristic of this flavor is by making the memory access really hard. Okay, great. Now we're talking about eavesdropping attacks. So quickly on eavesdropping attacks, this is where you have the prover and the verifier. Prover sends data, right? Verifier sends data back. And the eavesdropper is monitoring this conversation. So the first approach here is a hash one-time password, HOTP. These require both state and secret keys. And both the prover and verifier maintain counters. The prover sends the verifier a hash of the password with its current counter and the counter, and then increments the counter. And then the verifier checks that that password works and increments a counter. So let's look at that. Let's see what that looks like. So these look like this. So you have the prover, you have the verifier, and they have the secrets key. They have the secrets key, and then they compute, right? They send H of the secret key and I. And they send I to the verifier. The verifier then computes the same thing, and then they both increments I by 1. The problem with this is we're introducing state, right? There's your state right there and right there. And that's kind of hard to keep track of. So this is possible, and this works, but its weaknesses is this synchrony problem, and passwords are valid until you increment the counter. So if you might be able to reuse a password maliciously somehow, which isn't good. So that's the problem with hash-based one-time pads. Next, we have time-based one-time pads. This is where the counter is based on time and incremented based on that. When the user tries to authenticate, the server calculates the counter based on the current time, and then the user sends the hash of the password in the current time. So if we go back here, right, they send the hash of the secret key and the counter, but the counter is just a function of the time. So that's a time-based one-time pad. Lots of phone apps work this way. The weakness of the system is that it requires this kind of time situation, and once you generate the password and you can figure out the timing function, it's got a weakness there. But it doesn't require synchrony, which is quite nice. But it does require secrets. The next form of attack are active attacks. The way these active attacks work, there's a system called S-key. Sorry, this is how you're pretending it's active attacks. Active attacks, remember, are you have the prover and you have the malicious verifier who then leaks secrets to the malicious prover against the honest verifier. So this is how active attacks work. They leverage the concept of hash chaining. Hash chaining says like h to the 2 of x equals h of x. So the secret key is sampled. The way this works is you have the everyone knows the secret key and n, and the verifier knows the hash of the secret key up until the end. And then to authenticate, you send H, so you send one less hash of the secret key, and then the verifier takes that one less hash, and they actually hash that one more time to get the secret key, and then they authenticate, and then they decrement the counter by turning this into the new password. So then the next time you send a password, it becomes H to the n minus 2 of the secret key, which verifies against H to the new verification key, which is H to the n minus 1. So to kind of write that out, the verification key is given in the clear, and to authenticate, the prover sends one previous hash, then the verifier hashes it one more time, and sets the new verification key to the most recent proof by the prover. And the security of this rests on the fact that hash functions are irreversible. So that's a quick overview of these various login systems. They are extremely interesting. I think well worth exploration, and I think are quite thought-provoking. So thank you so much for tuning in to the lecture.